Hello everybody. Today we're going to we're going to work a little bit on a project. I've actually already been working on it, and that's this little setup here, which is a Joule Thief flashlight. I'm going to be building the classic Big Clive style Joule Thief. We'll put a link to his authentic Joule Thief video right there. But I've just been playing around with them kind of to get an idea of how the circuit actually works and what kind of limits you can stretch it to, and just basically learning how the thing works. So I'm going to demonstrate this one because it's my prettiest one so far. I've made 5 so far. We're going to make a 6th. So basically, this is a flat battery. I think it's about 0.8 volts currently. So it doesn't have enough energy in it to even light a little tungsten lamp, much less an LED. But if I turn this on, oh, the switch seems to be malfunctioning. That's distressing. Oh. It's not malfunctioning, I was putting in the LED backwards. So, anyway, you'll see that maybe the switch is malfunctioning. Oh, bugger. I'll have to work on that a little bit, figure out why that switch is being difficult. Anyway, so this is a white LED. The forward voltage of that is about 3 volts. But this battery is only at about 0.8 volts. Actually, I can quickly test it now that it's under load and see what its voltage actually says it is. So let's see what this battery's voltage is. It says 0.6 volts, so it's actually quite low at this point. So 0.6 volts, but it's powering this LED. And the way it's doing that is by using a little hand-wound inductor, and I'll talk about that one in a little, or hand-wound transformer, not inductor. It's using that with some feedback, and we'll talk about the circuit in just a few moments here. But it's basically flashing the LED on and off really fast. So if I set this to frequency counting, we'll see that the LED is actually flashing at 56-ish kilohertz. So it's flashing very, very rapidly. It's even at 60 frames per second. Maybe there's a little bit of shimmer if I wiggle it back and forth, but you know, it's absolutely imperceptible, and it seems to glow just as brightly as any LED would normally. So let's have a look at the circuit real quick. So the way this is made, I'll just use this pencil, is we have your voltage coming in here, generally about 1.5 volts if you're using a cell, 1.5 volt cell, and it comes in to this inductor that's been hand wound like so. Same number of windings on both sides with an iron core. But here's the significance. Those windings actually go in the opposite direction, and that's why you use these 2 dots to signify that they're going in the opposite direction. Now this is going to come down to a 1K resistor, and the value of the resistor is mostly arbitrary. And then we're going to come down to a PNP transistor, or an NPN transistor, sorry, that's not pointing in. And then that goes down to ground. And then across this, the collector and the emitter of the transistor there, we have the LED. That's a very simple circuit. So, what's happening here? Well, when you first turn on the circuit, you get some current that starts to flow down through this coil, and at this point it's not really acting as a transformer. But current starts to flow down, goes through this resistor, into the base, and down to ground. That starts to open the gate, or open the gate, that's a MOSFET term. It starts, I like to refer to these as gates. You apply power to the base, and it opens the door so that current can flow from the collector to the emitter. Anyway, so current starts to flow from the base, and then you start getting current flowing through this inductor, this side of the transformer, which is an inductor on that side of the transformer. It's two inductors smacked up against each other. So current starts to flow through this inductor and down to ground. That makes a magnetic field starts to build up in this side of the transformer, which crosses this side of the transformer. And because the windings are in the opposite direction, it actually cancels out the current flow here, which closes the base, and then current stops flowing and the magnetic field here collapses. When the magnetic field on this side of the transformer collapses, the voltage spikes upward very sharply, and when it exceeds the forward voltage of the LED conducts, it flashes, and then this field collapses, and then current starts flowing through here again, because it's not, this inductive field isn't creating a current flow in the opposite direction. And then that process repeats. So it pumps back and forth very rapidly, as we saw, about 60 kHz with the inductor that I wound. Another one, because I ran out of the small inductors that I salvaged out of CFLs, another one I wound this really huge inductor. This one oscillates at 100 kHz. But it doesn't seem any more efficient than these ones, which only have 9 turns. That one has 70. They still drag the battery down to about 0.3 volts, and I keep overdriving the mic here, so I'm going to bring the gain down a little bit. There we go. So yeah, more turns doesn't seem to affect the voltage at which it stops functioning. It just makes it oscillate faster. Anyway, so that's a brief discussion of the circuit. When you visit the link to Big Clive's video, he goes into much more detail about it. So I did a live stream on these, and I should have saved one to do for myself, but you'll see it in Big Clive's video, where you take a piece of magnet wire. I think I have a piece here that I can demonstrate. You take a piece of magnet wire, you fold it over very sharply, and then you start wrapping those two wires around the toroid until you can't fit wire through it anymore. Then you nip it off, you do a continuity check, you solder two opposite ends of the transformer together, leave two ends free, and then you have your little transformer built. So basically what I wanted to do for this video was just talk about the construction process that I was doing to build these little flashlights. So I'm going to dab a little bit of super glue gel there, and then just slap this inductor on, and I'm putting, or transformer, why do I keep saying inductor? I'm putting the two leads that are soldered together on the side closest to the positive here, because this is actually where the positive lead is going to attach. And then you'll need a NPN transistor. I'm using a 2N222, yeah, 4 twos for mine. It doesn't matter what kind of transistor you use. When I was running my testing, I used about 4 different NPN transistors, and none of them seemed to increase or decrease the efficiency of the circuit appreciably. you'll want a 1K resistor to control the flow of current to the base of the transistor. In my case, because it's being powered up with a switch, you'll need a little switch, an LED, and I'm doing a little something extra. I'm using these little power connectors here that I ordered on eBay, so that when I take these into class on Friday, I'll be able to ask people what color LED they want on their flashlight, and quickly bash them together right there during class. So this is taking a long time to set because I used a little too much super glue. So I'm just going to briefly pause and be right back once the super glue is set. Alright, we're back. I took the liberty while we were... Boy, I'm still overdriving that mic a little bit. All my previous videos have been too quiet, so now I have to try to bring the gain up a little bit so that you guys can actually hear me. Anyway, so I took the liberty of soldering on the transistor here. You'll see I soldered it on flat side down, and that's because it makes it convenient for attaching the negative lead of the battery terminal to the emitter, which is this leg, and then the LEDs just attach to the two legs sticking up there as well. So we're going to take this wire from the transformer and just kind of monkey it around here until it's laying up against the collector. And then we'll just, because I've already pre-tinned these wires, we'll just reflow solder on those wires and solder that on just like that. Then the next step is I'm going to trim the base of the transistor really quite short here, just like that. And then I'm going to also trim this resistor quite short, just like that. Then we'll just quickly dab a little bit of, still in shot here, right? Yep. We'll just quickly dab a little bit of solder onto the end of that resistor there. Dab off the excess, and then flow the resistor onto the base, like so. Then oops, I did not flow that on as well as I had hoped. Let's put a little more solder onto there, and just to encourage it to stick a little better, we'll dab some flux on. There we go, much better. Alright, so now what I like to do is we're going to bend this resistor kind of down and out of the way and meet it up with the other leg of the transformer here. So we're just going to kind of jockey the wires around a little bit here, make sure they're nice and touching. I'll dab a little bit of flux, and then flow those wires together. So we took one end of the two ends that were remaining, we soldered, and it doesn't matter which side you use as long as one side goes to one and one side goes to the other. So we took one side of that transformer and we soldered it onto the collector pin of the transistor. Then we took the other leg of the transformer, soldered it to the 1K resistor, which is then soldered to the base of the transistor, just Just cleaning up a little bit of a solder spike there. And then I'm going to go ahead and crop these fairly close. There we go. Because we want all of this to be very compact and tight, so that it takes up as little space as possible. So the next step is going to be to solder the positive lead onto the two ends of the transformer that were soldered together before. I actually did a live stream where I built a bunch of these, tested them, so you can go watch that live stream if you want, or I also highly recommend going to Big Clive's video, because he actually invented this particular form of the Joule thief, which is used absolutely everywhere. I've seen Joule thieves in dollar store solar lamps, and they're very clearly built off of Big Clive's concept for the Joule thief. So it's really interesting. He's just this humble electrician and YouTuber, but he's got this design that is just absolutely everywhere. It's very common in LED lights, little solar LED lamps, because it's a really great way of pushing a low voltage higher than what you would expect. Because the way inductors work, when the magnetic field collapses in an inductor, you actually end up with a pulse of voltage that can, on paper, actually be infinite. So I'm just going to take the two tinned ends here and flow them together. They didn't flow together very well, so I'll put some flux on. But yeah, but to keep the way we have the LED across the collector and emitter of the transistor, why is this being difficult? I'm going to have to push on that with something not heat conductive. The LED actually clamps that voltage spike to the forward voltage of the LED. Let's see. It looks like it's working fairly well. These aren't the most elegant LED flashlights in the world, but it's nice and compact, which is what I was after. So the next phase is to put this little connector onto the legs of the transistor. And I probably should have done this off screen, because my cutters are not performing very well anymore. I need to get a new pair, I think. But the channel's budget is currently somewhat thin. Alright, this is being very difficult. I basically crimped it. Now I can just sort of bend it back and forth to get it off. Come on. Alright. Yep, it's time for a new set of cutters. To try to work those into the budget at some point. But at least I can crimp the metal here, and the reason why I'm cutting these little bits off is they're actually meant to be crimped on with a crimp tool, but along with the greater majority of the rest of my equipment, I will probably never see those particular tools again. Alright, so we've now got these two pieces which we're going to solder onto the legs of the transistor. So I'm just going to take that toothpick, slide it through the springy part and flow some solder onto the clip. The toothpick just holds it upright while I'm putting the solder in. There we go. Alright, now I want to crop these a little shorter. So we're just going to kind of nip these off about here. That should be good. And I want to put the let's see. Yeah. I'm going to put them on like this. So I don't have a pair of pliers or tweezers readily available, so I'm just going to use my diagonal cutters very carefully here and flow that onto the lead. Just like that. Oops. That'd have been done 10 minutes ago if I had my crimp tool, but I suppose that's life. Maybe if my budget permits, I can order another. Oops, another one off of Banggood. So that's where I got my initial one. Alright, that's almost good. Oh, that didn't work at all. Oh, I've forgotten a step too. I should probably do that. Okay, so we're going to actually leave that one off for the moment and do the steps that I skipped. I'll just turn this off and move it off to the side for a moment. So now we need to actually put this switch on, and this was actually a 3-pin switch, so it was a DPST switch, but now I've clipped one of those leads off to make it an SPST switch. So what I'm going to do is I'm going to take my knife here and just kind of scratch up the side of the switch here. Like that. Sorry for the noise. And then I'm going to mar up the plastic right about here a little bit. This is an important thing because it gives the super glue a place to grip. Of course, I'm going to be encasing all of this in resin a little bit later, but this is just to kind of hold it in place while we solder it and get everything set up. So there's that in place. Now I'm going to take this negative lead and measure it out to about there. Crop it off. And strip it. And then I also want to crop these off to about half their length. Just like this. There we go. Oh, take a little bit more off of that one. There we go. Alright. I guess I shouldn't have shut off my soldering iron because I need it again. Alright. Next, now we have to wait for it to come to temperature. Gonna tin this wire. I'm gonna tin that leads of the switch. Alright, now we're going to take this wire, bring it up. Oop. Big blot of the solder there. Let's make that go away. Alright, so now we're going to bring this up. It's a pretty tight fit, but that's what I wanted. Bend it over just a little bit. Bend it a little bit more. Alright, that's pretty good. Now I just have to jockey it into position. Come on, cooperate. There we go. I'm not pleased with that. Let's try this again. So I want this to be fairly tight. Let's crop off a little bit of that wire. It can be a little fiddly getting the lengths all optimized, but here we go. So we'll just reflow that. There we go. Excellent. Alright, now we're going to take the other side of this, and it's already been tinned because it's the end that we cut off. So we're going to nip that down so there's just a little tiny bit sticking off, and flow it onto the other terminal of the switch. I'm not particularly sanguine about that soldering job, so I'm going to dab some flux on there to make it flow a little better. There we go. Yeah, much better. Okay, beautiful. So then we go and finish the part that I forgot to do, which is solder the negative lead of the battery onto the emitter of the transistor. Oh, crud. Well, good thing I have extra wire. Alright, so let's try this again. We're gonna strip that. Tin it. Oops, there we go. Crop it nice and short. Flow it onto here. Not sanguine about that again. There we go. Alright, let's try this again. So, measure it down, crop it off, carefully strip it. There we go. Tin this wire. Bring it in. Oops. and float on. There we go. And then we can grab the pin for the connector and solder it into solder it into place. There we go. There we go. Alright, now we just have to kind of jockey these around a little bit, make sure they're into place, and then we're going to slide the connector on, and it clips into place rather nicely. Perfect. Alright, and then we'll take an LED and pop it into here with the negative lead over there. And where'd that battery go? It's over here. Today's awkward jump cut is brought to you by me not paying attention to what I was doing, and the maximum video length was reached, which means this video is actually running quite long. Anyway, so here's the one we just built, and we'll go ahead and whack an LED in there, click it on, it's working. So, just like I've done before when I was talking to nothing, we'll take a frequency count. It's running at about 43 kHz, which is, was, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 turns of the magnet wire. But here's a weird thing. I'm not entirely too sure why this happened. I think I may have messed up the windings on this one. But if we whack the LED into this one, I'm not too sure if the microphone is picking that up. But it whistles. And if we put the frequency count on this one, it's oscillating at 11 kHz, which is an audible frequency. So you're actually hearing the inductor or the transformer oscillating. And then this one, because I ran out of the small inductors, or the small ferrites, so I moved to the really big toroid that I had. We'll go ahead and whack the battery in there. And this one is oscillating at 140 kHz. The last time I measured this, it was running at 100. So very, very high frequency on that one. But it's not linear. This one has 70 turns, but it's only running about 3 times the frequency for 7 times the turns as the other ones that are running at about 50 kHz. So that's kind of an interesting thing. Anyway, thanks so much for watching me ramble on this video. If you haven't already, consider clicking here to subscribe. Over here will be a video that YouTube thinks you'll find interesting based on your watching habits. Right over here will be my prototypes playlist, and right here will be a link to my Patreon that you can use to help fund more projects like this. Anyway, thanks so much for watching, and we'll see you whenever I upload next. Bye-bye.